Alright, so today we're going to be talking about balancing chemical formulas. So the basic thing you just have to remember is that matter is neither created nor destroyed, and also during a chemical reaction, elements do not change into other elements. So this means that we can very easily state that atoms are neither created nor destroyed during a chemical reaction. Also, and basically by putting together these two laws, we can come up with another expression that explains how chemical reactions work. So the number and types of atoms on the left-hand side must be the same number and types of atoms on the right-hand side. And that's because since atoms are neither created nor destroyed, all that's going on during a chemical reaction is that they are just getting rearranged. You're still going to have the same atoms, they're just going to be connected to different things, but there is no destroying of matter. If there was, that would be a nuclear reaction, and that is not what we are dealing with here. So the way we write out chemical reactions is like this. So over here we have the reactant, so whatever we're pouring into the beaker, whatever our reaction vessel is, and then they are reacting under certain conditions, okay, and producing the products that we are interested in. Now these conditions here may or may not be listed. Many times they're just left off if the reaction just pretty much goes when you just mix the stuff together. So the conditions over here could be if we're dealing with things like heat, that's commonly represented by the Greek letter delta. Light, commonly just represented by H nu. These are for things like photochemical reactions, so they need light to get them started. The temperature, maybe this is under hot or cold conditions. Pressure, maybe this only happens under high pressure conditions. Is there a catalyst involved? That's something that speeds up the reaction. And there could be other things as well, but these are the typical ones. Another way you can also see these reactions is if the reactant doesn't all go to the product. So we could have here. Now over here, if we have an arrow pointing like this, that means that all your reactants go into the products, and there is no reverse reaction. So products don't start going back into forming reactants. But over here, where we have this double arrow, the reactants can form the products like usual, but sometimes the products can break down and form the reactants again. Okay, and these are very common, especially if we're dealing with equilibrium systems. For instance, like a weak acid. We might have, here's the acid in molecular form. It breaks up into the ion and the anion, or I should say the cation and the anion, and then those cation and the anion can form back to make the molecular acid again. So we'll be seeing both of those types of reactions in the future here. Alright, now as for balancing reactions, well, they're actually fairly simple. Let's say we have here, I'm just going to write this out in words, let's say we have here hydrogen, and we're adding oxygen, and we're forming water. So this is essentially what you're doing when you're reacting things. But of course, if you're doing this reaction, we want to write out the molecules. So I have here H2 plus O2 give us H2O. And remember, hydrogen and oxygen, those are the Hunkelbrief molecules. They're always going to be diatomic. So if you see here hydrogen, that means H2. If you see oxygen, that means O2. The only time that you would have monoatomic oxygen would be if someone said up there atomic oxygen or atomic hydrogen or monoatomic hydrogen or oxygen. But if you just say regular hydrogen and oxygen, this is what you mean. Like we said up here, number and types of atoms have to be the same on both sides, right? Well, here I have two hydrogens, that's good. Here I have two oxygens, here I only have one. So the first thing you notice is, well, I gotta go here and obviously just make this a 2. So when I put the 2 in front here, that is basically multiplying every atom in here by that factor of 2. So now I'm going to have here my two oxygens. I have two oxygens, that's happy. But over here I'm going to have 4 hydrogens. Over here I only have 2 hydrogens, so I have to multiply this one by 2 to make that happy. And now everything's nice and happy, right? I have 4 hydrogens, 2 times 2, that's 4. 4 hydrogens here, 2 oxygens, and 2 oxygens. So that's a smiley face. Now, just one thing to note here, when you're dealing with a reaction like this is the way the reaction works out. However, it does not mean that this is actually what happens. You do not have 2 hydrogen molecules colliding with an oxygen to make 2 water molecules at the end. All right, this is not the mechanism. This is just, the overall reaction. Now, what I was saying is that it's not the mechanism of the reaction, it's just, the elements that are actually reacting together. Well, this is what actually happens when you mix together hydrogen and oxygen gases. And you probably may have seen, the gigantic explosion. Well, what happens here is, for instance, here we have the hydrogen and the oxygen. There is an initiation step in which they bump into each other with enough energy, and they form two OH radicals. Okay, this isn't a hydroxide anion. This is just an OH molecule. We call it a radical because there's an unpaired electron, and it's much more reactive than a regular molecule. So this is called an OH radical. So we have here two hydrogens and oxygen give us two OH radicals. Now this OH radical undergoes a propagation step where it goes through here and basically forms our product. So the OH bumps into another hydrogen and forms an H2O. Then what happens is there's also a hydrogen atom which is formed, and this yields over here to form a branching step. So once you have this hydrogen atom, now it bumps into an oxygen molecule, forms another hydroxyl radical, then of course that can go up there. And then this oxygen goes down here, reacts with another hydrogen to form another hydroxyl radical, and then that hydrogen. And this is this branching area right here, and this is the whole reason why oxygen and hydrogen, when you mix them together, they react explosively. Because look what happens. Well, first of all, you get these two and you form two OHs. Okay. But then every OH goes here, forms a hydrogen, and then this hydrogen, when it goes through here, forms two hydroxyl radicals. And then it just keeps going on, and then it forms another two, and another two, and another two, and of course then you have these coming out here. So essentially this reaction and all these little radicals over here propagate exponentially. So instead of like a nice normal reaction where you just have one thing reacting and going to the product and that's the end of it, and actually as you can see here, this propagation is exothermic, meaning that it gives off a lot of energy, and it is also fast because these third and fourth reactions, so these two in the branching areas, there's two radicals formed from one. So essentially you're going 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and so on and so on. So essentially it's growing exponentially right here. And so right here, if the rate of branching is greater than the rate of termination, and this is the termination step, essentially we have these hydrogens going here and they just keep branching out more and more and more, but occasionally the hydrogens are going to run into something and just stop. And as long as this branching here is greater than the termination, then the number of radicals increases exponentially with time, and then you get an explosion that results. And we won't get into this here, but this is actually looking at explosive limits of oxygen and hydrogen mixtures. So at different pressures, you could actually explain a lot of the kinetics here, why for certain pressures up here there is no explosion, but then at these other pressures there are actually explosions. And a lot of that has to deal with the fact that we're dealing with this whole branching stuff here, and basically the propagation and termination steps. So the formation of water and the kinetics of this is actually a very, very interesting field, and there's a lot of interest into all of this. And also, this over here, if this actually did occur, this would be what we would call a trimolecular reaction, and those are actually very uncommon, because what you have to do here is have two hydrogen molecules and an oxygen molecule hit each other exactly the right energy, exactly the right time, exactly the right angles to actually undergo this reaction, and that is extremely unlikely to actually happen. Most of the time when you have any reactions, it's going to be one thing bumping into another. There are some reactions, and if you look them up you can probably find where you do need three molecules bumping into each other at the same time, but those are few and far between. All right, and usually any time you see a reaction like this, that does not denote the mechanism. That is just telling you how much reactants and how much products you're actually going to be making. Okay, when you are balancing these things, use whole numbers. Fractions are basically just messy. They're not wrong, but they sometimes can look a little messy there. And if you do have a fraction, just multiply through by the denominator, and then you can make everything a nice round integer number. So for instance, for right here, I could have went here, one hydrogen, half of an oxygen gives us a water. That would be fine. It would still be balanced, but it would just look kind of messy. When you have those like 3/7 or something, it just looks weird. So always just best to kind of just stick with a nice whole integer number there. And also when you have these, know that water, H2O, is not the same thing as hydrogen peroxide, H2O2. So when you're given a reaction that's hydrogen plus oxygen gives you water, don't try balancing it by putting a little subscript there, because that's just going to be very wrong. So here, hydrogen plus oxygen is water, not hydrogen oxygen gives you H2O2, because that, will simply just not work. Now, when we're going to be dealing with these reactions, commonly what's going to be put on these reactants and products as well is the physical states that they are actually undertaking. There's 4 basic states here: gas, liquid, solid, and also aqueous. So G is for gas, that's pretty self-explanatory. L is for liquid. Now, when we're talking about liquid here, we mean a pure liquid. Such as, we're making water, or we're making ethanol, or burning ethanol. That's the pure stuff right there. There's nothing mixed in, and you'll see why in a minute. And then S is for solid. Again, pretty self-explanatory. Now, this is the one down here, aqueous. And what this means is, so aqueous means dissolved in water. All right, and this is, for instance, if I take sodium chloride, which would be aqueous, and this is just salt water. So if I take solid sodium hydroxide, or solid sodium chloride, add it to water, we get salt water. However, liquid sodium chloride, that would be 800 degrees Celsius molten salt. Okay, very, very different. So most of the time we'll be dealing with aqueous, and we'll get into the whole solubility rules in an upcoming video here. And really, aqueous, you'll be seeing this quite a lot because, a lot of the reactions that we deal with happen in water. And it's really just the ions and whatever is dissolved in there. So we see this also with acids and bases and salts very, very commonly. All right, and here's an example. If we take sodium metal, so sodium metal solid plus water, that's a liquid. And this is going to form sodium hydroxide. That's going to be aqueous, plus hydrogen, which is gas. So this reaction right here has all 4 phases in there. You have sodium solid, water, plus sodium hydroxide, plus hydrogen. Now, as you can see, hopefully, that this is not actually balanced. So again, just a good little practice for this. So here, my sodium, yes, that's fine. Here I have 2 hydrogens. Here I have 1 and I have 3, so that's obviously not balanced. My oxygens are balanced. So I'm going to have to move things around here. And if you look, well, there's 2 ways I could do this. I could either just put a 2 here, or I could put a 1/2 here. What I'll actually do, again, just to avoid the whole fraction stuff, I'll just put a 2 over here. Of course, once I do that, this means that I now have 2 oxygens and 2 sodiums. Well, I can fix the sodium real quick. And I'm going to need 2 oxygens over here. And now, I believe that should be good. So that's going to be 2 sodiums, 4 hydrogens. That's 1, 2, 3, 4. And then 2 oxygens, 2 oxygens. So yeah, now this is nicely balanced. All right, and just a few more little examples here just to bring the point home. Another common chemical reaction that we'll be seeing quite often is a combustion reaction. So here we'll take methane plus and methane is a gas, by the way, plus the oxygen. This is also a gas. And this is going to react to give me carbon dioxide, which is a gas, plus water, which is a gas. Now, you might be saying, wait a minute, I thought you just said right up here, water, that's a liquid. Well, why are we putting this as a gas? Well, all these things that we're dealing with here can exist in multiple phases, right? Methane, if you cool it down enough, will be liquid, and if you cool it down even further, it will be a solid. Same thing with the oxygen and carbon dioxide and water, right? It can be a solid, liquid, or a gas. But here, this is a combustion reaction. We have things burning. If you have a natural gas stove, you know this. So what happens, of course, if you're reacting the methane and it's burning, you're making water, it's hot in a flame, you do not have liquid water coming out. So the water that comes out of here is going to be in the gaseous form. So, just be aware, any of these can take on different phases. Most of the time it'll be specified, what actual phase is coming on. But, so occasionally you just have to use a little common sense and figure out, what the phase should be. All right, so again, this isn't balanced. So here I have 1 carbon, right? I have here 4 hydrogens. I have 2 hydrogens here, so I need to put a 2 there. So I have 4 hydrogens here. And then I have here 2 oxygen on this side. I have 1, 2, 3, 4. So that means I'm going to need a 2 over here. And now that should be all happy. So 1 carbon, 4 hydrogens, 4 oxygens, 1, 2, 3, 4. And that's the basic combustion reaction of methane. Now, let's say you have low oxygen in your house, which can sometimes happen, and you get incomplete combustion. This is why we always have to be aware if you're burning gas in a confined space, because you can actually make carbon monoxide. So here, if I take methane again, plus the oxygen like we did, But now this is going to be in a low oxygen environment, so I'm only going to be making carbon monoxide plus water. And again, all of these are going to be a gas. All right, so we balance this. 1 carbon, that's fine. Here I have 4 hydrogens. There's my 2 on this side, so again, same thing. But now here I have 2 oxygens. I have here 1 oxygen, and I have another 2, so that's 3 oxygen on this side, 2. So what I could do is I could just balance things once at a time, but what is actually a little bit easier is if I just go here and say, well, that could be 3 halves of an oxygen. Now, remember we said fractions are messy, and in this case, what you would just do is just multiply the entire thing through by 2. Okay, so I'm just going to multiply everything down here by 2. So what we'll get is going to be 2 methanes plus now 3 oxygens, and that's going to give me 2 carbon monoxides, plus now 2 times 2, that's going to be 4 waters. All right, and just to verify, there's two carbons, 8 hydrogens, so that's 2 times 4, and over here 4 times 2, that's 8 hydrogens, and 3 times 2 is 6, that's 1, 2, plus another 4, that's 6. So everything is balanced over here, and we're happy. For once, I think this will actually be a short video, so I will stop it there.